Okay, so you remember I told you about this theorem, and we kind of started the proof a little bit. So let me just remind you what it was we were trying to prove. So the claim in this theorem is that if you choose some prime p and some integer m, it is possible to construct an infinite word that avoids all repetitions of exponent 1 plus 1 over p to the m in all arithmetic subsequences where the difference of the arithmetic progression is not a multiple of p. Right?
It's true that in this theorem one can choose m equal to 0 and avoid squares in all progressions except for some arbitrarily chosen p.
Yes, so okay, so if you choose m equals 0, and well, if you choose m equals 0 and p equals 2, or then you get this. You avoid squares in all arithmetic progressions of odd difference, and then if you choose some arbitrary p, then you will avoid squares in all arithmetic progressions except those multiples of p. And that's correct. So, but for larger p, the alphabet size you will need will be bigger, right? For p equals 2, you get 4-letter alphabet. For larger p, you will need a larger alphabet because, let me remind you the construction. So, we first define q to be p to the m plus 1. And this is our alphabet, right? Our alphabet are these numbers between 0 and 2q squared. Right, so if p is larger, you need, of course, a larger alphabet here. Right? And so now this is the rule. This is the rule to define the nth term of this sequence. Right? So if n is not divisible by q, we just take n mod q squared. If n is divisible by q, then we take this part n prime mod q squared, and then we shift by q squared. Right? So that's the construction. This is what it looks like when m is 0 and p is 2. We get this sequence over the alphabet 1, 3, 5, and 7. Right? Okay, so I think this is as far as we got last time. I showed you the construction, what it looks like. We didn't do the proof. So, okay, here's the proof. So this is just reminding you of the construction we just saw. And so the proof is by contradiction, right? You suppose that there is this kind of repetition in some arithmetic progression where the difference is some number k, not a multiple of p, and then we try to get some contradiction. Okay, so let me write down what this repetition looks like. Okay, so first of all, it is in some arithmetic progression of difference k, right? So I have some subsequence starting at position I, then I plus k, I plus 2k, I plus 3k, and so on. And now what is a 1 plus 1 over p to the m power going to look like? Well, I'm going to have some block of length, let's say s. It will repeat again later on. This block of length s will repeat again later on at a distance r. And the ratio of s over r should be bigger than 1 over p to the m, right? So this is a 1 plus 1 over p to the m power, and it's in this arithmetic progression, right? So I have this equation here. So let's look at the first, so I have this ai equals to ai plus rk. So let's look at what the value of that can be. Okay, it's either going to be bigger or smaller than q squared, right? You remember the construction, it had two cases. So in one case, if it has a value bigger than q squared, then that was because I and I plus rk are divisible by q. Right? That was one case of the construction. In the other case, if these are smaller than q squared, well then the construction said that these things must be congruent mod q squared. Right? So in either case, we get that rk is divisible by q. But q is a power of p, k is not divisible by p, therefore r is divisible by q. Right? So that's the first thing. R is divisible by q. So write r as some power of q times some r prime that is not divisible by q. And now we get some inequality here. Right? So remember, S is the length of the repeated block. R is the distance between the two repetitions, and we had that S over R is at least 1 over p to the m. Of course, by definition, Q was p to the m plus 1. So we substitute in this for R, and we get the following inequality, right, after we simplify. S is bigger than p times q to the L minus 1. Okay. So now the point is that these positions, I plus k, and so on, there are S of them. And of course, k is not divisible by p. So this sequence of numbers, it forms a complete set of residues mod p times q to the L minus 1, right? Because there are S of them and they're all relatively prime. So this is a complete set of residues mod p times q to the L plus 1. Therefore, there must exist one of them congruent to this value, mod p times q to the L minus 1, right? Because all of them are there, so I can find certainly one congruent to this. So let's write it out. J is congruent to q to the L minus 1 modulo p times q to the L minus 1. And we simplify a little bit. We do the same thing for j plus rk. Here is j, this is r, this is k, and we simplify a little bit. Okay? Right, remember, j is some position in the first block, j plus rk is the corresponding position in the second repeated block, right? So of course, because this is a repetition, these are the same. And therefore, these j and j plus rk, they must be congruent mod q squared. Therefore, if we cancel this AP plus 1, we get that q times r prime times k is congruent to 0 mod q squared. Okay, but then the only way this can happen is if r prime times k is a multiple of q. Q is a power of p. K is not divisible by p. Therefore, r prime should be divisible by q. But the definition of r prime was such that r prime is not divisible by q. Right? So that's the contradiction. Right, we have r prime times k is 0 mod q. K is not a multiple of p, and r prime is not divisible by q. So we get a contradiction. Right, so that's it. We get a contradiction here, so this repetition does not exist. And that completes the proof. So, well, maybe it's a bit technical, but, well, if it's a very strong and surprising result that you can avoid these repetitions in all of these arithmetic progressions, except for some small exceptional cases. So it's a bit surprising that the construction is relatively simple. So let's again look at this special case where we take p equals 2, m equals 0. The alphabet size, as we have seen, is 4. We use an alphabet 1, 3, 5, and 7. And this is the word that the theorem produces. Now, suppose we do this relabeling. We relabel 1 and 5. We map those to zeros. And the 3s and the 7s, we map those to 1. Okay. So this is the infinite word that we get now over 0 and 1. So this is actually a well-known classical word, right? This is called the paper folding word. And it's a well-studied word. If you want to know why it's called the paper folding word, you take a piece of paper and then you fold it in half like this, and then you fold it in half again, and you fold it in half again and again, and you fold it infinitely many times, and then you unfold it, and then you look at the pattern of, you will have some peaks and some valleys, and you write down 0 for a peak and 1 for a valley, or the other way around, and you get this sequence, right? So that's why it's called the paper folding sequence, and it's quite well studied. You can use it to draw some nice fractal dragon curves. It also has some applications in continued fractions, and so on. And here's another construction of this same word. This is another very nice construction of infinite words, so-called tuplets construction. And the way this tuplets construction works is you start with just an infinite sequence of gaps, and then you want to fill in the gaps in a certain way. So what you do is you fill in every second gap by the alternating sequence 0, 1, 0, 1, 0, 1. Right? So you go 0 gap, 1 gap, 0 gap, 1 gap. You fill in the gaps like this. And now you do the same thing in the remaining gaps. Right? You fill in a 0 gap, 1 gap, 0 gap, 1 gap. You get this. And then you do it again. You fill in the gaps. Right? And you will produce this infinite word. This is the paper folding word. So if you always fill in by the periodic sequence 0, 1, 0, 1, 0, 1, you will get the paper folding word, or the ordinary paper folding word. But if you change your mind every once in a while and you fill in 1, 0, 1, 0, 1, 0, then you will get some other kind of paper folding word. Right? And basically it corresponds to folding the paper this way or folding the paper the other way. Right? So this is where this comes from. And so again, like I said, this is a classical word. It's been well studied. Of course, it's a binary word, so it will contain some squares, but it does not contain any big squares. So the only squares it contains are these small ones. Okay, so remember this construction of words avoiding repetitions in these arithmetic progressions. It has a very nice application to the construction of some two-dimensional words avoiding repetitions. All right, so okay, an ordinary word is just some sequence of symbols along a line, right? So a two-dimensional word is just a grid of letters, right? Two-dimensional grid of letters. Okay. if I have this two-dimensional grid of letters, suppose I draw a straight line through the grid of rational slope, and wherever that straight line meets one of the lattice points, one of the integer points on the grid, there'll be a letter there. And so I write down the letter. All right, so I have this straight line through the grid, and I get an infinite word by recording the letters that I encounter on this straight line through the grid, right? So, okay, I have these lines through the grid. So these two-dimensional words, they were at least introduced in that paper by Bean, Ehrenfurcht, and McNulty that I mentioned yesterday. They talked about two-dimensional square-free words, and for them, a two-dimensional square-free word is a word where you never see the same rectangle repeated next to each other. So this result that I'm going to tell you now is somewhat stronger than that. So this is from that same paper by Arturo Carpi. And the result is as follows. There exists a two-dimensional word using only a 16-letter alphabet, such that every line that you can possibly draw through this two-dimensional grid will give you a square-free word. Every line of any slope. All right, the horizontal, vertical, diagonal, any strange slope you want. These will all be square-free. These will all give you square-free infinite sequences. So it seems somehow like quite a strong result. But the proof is actually an immediate consequence of the result that we gave on avoiding repetitions in arithmetic progressions. So the construction is very simple. We take one of these words. So I take one of these sequences over a 4-letter alphabet that avoids all squares in all arithmetic progressions of odd difference. Right? So we've already seen what that word looks like. And now I make a new alphabet that's the Cartesian product of the old alphabet with itself. So this is my 16-letter alphabet. Right? And I make my two-dimensional word by simply taking the Cartesian product of these two words. Right? You see the letter in the position mn of the grid. I just take the mth letter of u and the nth letter of v, and I make that pair. That pair is one new letter, right? So that is the letter that goes in this position, right? So I make some Cartesian product of these two words, and I get this grid. And now it's immediate that that any line through this grid will be square-free. Because what happens? If I take a line, it looks like this, which I can translate into, okay, u runs through these values, and v runs through these values. My j1 and j2 are relatively prime. But because they are relatively prime, one of them must be odd, I can assume, right?
So does we consider all the rational lines?
Yes. Yes. Because, well, if the lines were irrational, then we would not encounter more than one lattice point.
Okay.
Right.
So okay.
Yeah. So it should be rational, so that we get infinitely many. We encounter infinitely many.
Points on the plane, drawn at some small squares, one by one.
Yeah. So this is just the integer lattice, and I want to pick a line that encounters infinitely many lattice points, so that I get an infinite word. So of course so now one of these two arithmetic progressions has an odd difference. And so if this thing had a square, then there would be a square in the first component, and that would be a square in an arithmetic progression of odd difference in u. Okay? So then this line is square free. Right? So that's the proof, right? We can construct these two-dimensional words that avoid these kind of repetitions in all lines of all rational slopes. Okay, so that was the first part about avoiding repetitions in arithmetic progressions. Now we move on to something new, a different type of repetition. So we've seen some generalizations already. We've seen, what have we seen? We've seen fractional repetitions. We've seen patterns with several variables. So these abelian repetitions is a different kind of repetition. So an abelian square, so an ordinary square is, I have the same word x repeated twice in a row. An abelian square is something that looks like x and then some permutation of the letters of x, right? So an anagram, right? So you can see in English this word reappear is an abelian square, right? Because reap, I take some permutation of it and I get peer, right? So okay, so this, the question whether are abelian squares avoidable over some finite alphabet, this was asked by Paul Erdős in 1961. So the first person to give a positive answer was Evdokimov in 1968. He constructed a sequence over 25 symbols that contain no abelian squares. And then some couple of years later, Pleasance improved this construction to 5-letter alphabet. So he did it over 5 letters. And then there were some other results about abelian fifth powers, abelian fourth powers, abelian cubes. Right, so it should be clear what I mean by abelian cube or abelian k power. Right, I have k blocks and each one of them is a permutation of the first one or of any one. Right? So we have some of these results here. So remember, abelian squares are avoidable over 5 letters. 1970 due to Pleasance. So of course the open question was, is 5 the smallest alphabet for which this is possible? The answer is no. It can be done over 4-letter alphabet, and this was proved by Karen in 1992. And well, his construction is not easy. It was found by a very difficult computer search. This word that he constructed is constructed by iterating a morphism, but the images of each letter in the morphism have length 85. Right, so each letter goes to something of length 85. So this construction was not easy to find. So let me give you an idea of how to prove some of these results about avoiding abelian repetitions. And the main tool, or the main concept that we need, is this so-called adjacency matrix of a morphism. So, okay, let's skip the technical definition. It's actually very easy to understand what the matrix is. We make a matrix whose rows and columns are labeled by the letters of the alphabet. And now in each column, we count the number of occurrences of A, B, and C in the image of A. In the second column, we count the number of occurrences of A, B, and C in the image of B. And the third column, we count the number of occurrences of A, B, and C in the image of C. Right? So we make this matrix, right? You can see in the image of A we have 1A, 1B, and 0 C's. Right? And so on. So we make this matrix, right? For any morphism from an alphabet into itself, we can make this matrix. So now we define this map psi. So this map psi in formal languages, this is called the Parikh map. Right? It takes a word and it produces a vector, the Parikh vector. So what is this vector? I have a word. This map psi produces a vector, and each entry of the vector is an integer that counts the number of occurrences of each alphabet symbol in the word. Right? So that's what this notation means here, right? Number of occurrences of the letter A1 in W, number of occurrences of the letter A2 in W, so on. Right? So I make this vector. And now, of course, the point is that if I have a word and I apply the morphism to it, then its Parikh vector can be obtained by taking the Parikh vector of the word I started with and multiplying it by the matrix of the morphism, right? So that's the point, right? If I have a word and I apply the morphism to it, then the new vector I get by multiplying the old vector by the matrix of the morphism. And so if I iterate a morphism, right? If I iterate some morphism phi, let's say n times, then the Parikh vector of this word I get just by multiplying the Parikh vector of the original word by the nth power of the matrix. So, okay. So now this is Decking's construction of an infinite binary sequence that avoids abelian fourth powers. Okay? So I have this binary sequence. I claim that it has no abelian fourth power. So let's see how the proof goes. The main idea of the proof is to come up with some kind of map from words into some finite abelian group in such a way that abelian repetitions correspond to an arithmetic progression in this abelian group. Okay? And then we show that in fact these arithmetic progressions don't exist. Okay, so that's the idea. Okay, so we need some technical stuff. So I have this morphism phi. Remember, I called the images of each letter, I called them blocks. The prefix of any block, let's call it the left subblock. And any suffix of a block, we call a right subblock. And like I said, we will have some abelian group, G. And a subset of G is progression free of order n if it does not contain an arithmetic progression with n terms. Right? That's okay? So now I define this map that I mentioned before. It's a map from words into this abelian group. And it should be a morphism in the sense that if I apply f to a word, I should be able to compute that by applying f to each letter and then adding them up. Right? So let's call this thing a weight function. So now let's look at some collection of blocks. And I've cut each block into some prefix and some suffix. You can see v1, v1 prime. One more definition. So this weight function f is called phi injective if it has the following property. If whenever I have f of these prefixes, if they're all the same, then either the prefixes are all the same or the corresponding suffixes are all the same. Okay? So I have some collection of blocks, I cut them into prefix and suffix. If the weights of all those prefixes are the same, then either the prefixes are all the same or the suffixes are all the same. Now, what's the point of that? If you remember the proof from yesterday about square-free morphisms, do you remember the basic idea of the proof? It was some proof by contradiction. I suppose I had a square, and then I looked at how this square could be parsed into blocks. And then I said, well, okay, maybe the square starts in the middle of a block and ends in the middle of a block. And then I should somehow try to shift the square so that it starts at the beginning of a block and ends at the end of a block. So I'm going to do the same thing here. I want to do this kind of shifting. And this is the technical condition that will let me do that. Okay, so this is the criterion for testing. Right? I have a morphism. I think that it generates an infinite word that avoids abelian fourth powers or abelian nth powers. How do I know? How do I prove that that is the case? I have this criterion. If this stuff is satisfied, then my word avoids abelian nth powers. So what are the conditions? So I need the matrix of the morphism to be invertible. I need the weight, I have this weight function. I need the weights of all the blocks to be 0. I need this collection of weights. All right, so I look at the weights of all the prefixes of all the blocks. Take that collection of weights, and this should not contain any arithmetic progression of length n+1. So if that happens, and if that weight function f is phi injective, if all of that stuff happens, then the word generated by this morphism avoids abelian nth powers. Okay? So here's how the proof goes. It's a proof by contradiction. So suppose there is an abelian nth power. So let's say n equals 3. So in my picture, I have this abelian cube, b1, b2, b3. Right? I have some abelian cube. Now, in the general case, look, here's this v1, v1 prime. So this is a block of the morphism. Right? These guys here. Right, so in the general case, my repetition could start in the middle of a block and could end in the middle of a block. And then somehow I want to shift and get a new abelian repetition, but just shifted a little bit. So that's these guys here, C1, C2, C3, shifted so that everything is aligned with the blocks. Right? That's what I would like to get. So, I suppose I have this repetition, and I suppose it's minimal. Right? So I want a contradiction, so I will contradict the minimality of this counterexample. Right? Now the point is, these are abelian repetitions. So what does that mean? That means that each block is a permutation of any of the other blocks. So that means that they have the same number of occurrences of each alphabet symbol. Right? But that means the weights of the blocks must be identical. Right? Because the weight of a block is just the sum of the weights of the letters, and we have the same number of letters of each kind in every block. So the weights of the blocks are all the same. I mean, the weights of these B's are all the same. Right? Now the weights of the images of the morphism, those were all 0. right? That was part of the condition of the weight function. Right? The weights of those images have to all be 0. So you can see that all the stuff in the middle of B1, like anything in the middle of B1 that is just complete blocks of the morphism, all of that has weight 0. Right? And the only thing that has non-zero weight is just this little piece here that comes from the V1 prime, and this little piece here that comes from this V2, right? Those two things have some non-zero weight, and then the stuff in the middle is just weight 0, right? Because the stuff in the middle is just complete blocks. Right, so the point is that because of that property, that in fact the weights of these prefixes will form an arithmetic progression. Right? The weights of this V1, the weight of this V2, the weight of this V3, the weight of this V4, they'll form an arithmetic progression. Right? Because the weights of the B's are the same, and the weights of all the stuff in the middle is just 0. So, these things will form an arithmetic progression with the difference f of whatever the BI's are. So, I have this arithmetic progression. Okay, but well, the point is that there are no arithmetic progressions, right? There are no arithmetic progressions of length n plus 1. Right? Except for the trivial one where, in fact, these are all the same. Right? So, in fact, the weights of these V's, these little prefixes, V1, V2, V3, V4, their weights are all identical. And now, by that phi injectivity, that means either V1, V2, V3, V4 are all the same, or the suffixes V1 prime, V2 prime, V3 prime, all those suffixes here, 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 here are the same, right? And so whichever case happens, I either now shift my repetition to the left or I shift my repetition to the right, right? Okay, so let's suppose that the first case happens. So now I shift my repetition, B1, B2, B3, I shift it to the left. And I get this C1, C2, C3. Now, everything is lined up with the blocks, and now I take a pre-image under the morphism, right? So, okay, I take the pre-image of these C1, C2, C3, right? These are all the image of some smaller word, D1, D2, D3, that occurs earlier in my infinite word, right? Because my infinite word was generated by iterating this morphism. So the pre-images of these CIs, they occur earlier in the word. And now the point is, okay, the C1, C2, C3 is an abelian repetition. Their Parikh vectors are all the same. But now what is the Parikh vector of their pre-image? I get it by multiplying by the inverse of the matrix, right? Here, right? The Parikh vector of CI is the matrix times the Parikh vector of DI. So Parikh vector of DI is I get by multiplying by the inverse. Right? And of course, one of the conditions of the theorem was that the matrix is invertible. Right? So that this works. And so now I take the inverse and I get that D1, D2, D3, they all have the same Parikh vector. And therefore, this is an abelian repetition, a smaller abelian repetition occurring earlier in the word, which contradicts the minimality of B1, B2, B3, right? Okay. So that's the method. Here's how it works on a specific example. Okay, this is the morphism that Decking found to generate an infinite binary word avoiding abelian fourth powers. You write down its matrix, 3 A's and 1 B in the first image, 1 A and 2 B's in the second image. Check that the matrix is invertible. Now we have to find the appropriate abelian group, and we take Z5 as our abelian group. How do you know what to take? Oh, you take the determinant of this matrix. You get 5. All right, so that's your abelian group, Z5. I need a weight function. So I say the weight of A is 1, the weight of B is 2. I have to check that the weights of the images are all 0 in Z5. So I can check 1 plus 1 plus 1 plus 2 is 0. 1 plus 2 plus 2 is 0. Right? The weights are 0 in Z5. I need to compute all the weights of prefixes. This is what I get. And there is no length 5 arithmetic progression in there. Check that. I need to check that F is phi injective. So I check that. I need to check that there are no very short abelian fourth powers. It's kind of the base case of the induction. And so now I check all of that. And this morphism satisfies all the criteria of the theorem. So therefore, the corresponding infinite word avoids abelian fourth powers. Right? So that's how it goes. So Decking also did the same thing for avoiding abelian cubes over a 3-letter alphabet. Here's the morphism. Theta looks like this. And you do the same thing. You just check that this morphism satisfies all the same conditions. And you get that this infinite word avoids abelian cubes. Right?
Is it over Z7?
I think so. I think so. I can't compute that determinant in my head. But I think that's right. So that worked for abelian squares, abelian fourth powers, abelian cubes. Like I said, for abelian squares, somehow this is very hard. And I told you already that Karenen's construction is it uses this huge morphism that he found by some very long computer calculations. So just a couple more things to finish up this abelian stuff. So of course, we started when we talked about squares and cubes, we generalized that to patterns with more variables. You can do the same thing for abelian repetitions, right? You can make abelian patterns. So let's say an abelian instance of the pattern x, x, y, x, y, x is a word that looks like this, where the x's, right, these big x's, they should all be permutations of each other, and then all the big y's, those should be permutations of each other, right? So you can make some patterns. So here's an example of a word that matches that pattern, right? I have x, 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 x. Those should all be permutations of each other. And then this y and this y, those should be permutations of each other. All right, so we can ask all the same questions about avoidability of patterns in the abelian sense. But in fact, this is very difficult. And there are very few results on avoidability of patterns. Very little is known, and the questions are quite difficult. Here's an example of a result that is known. If I look at binary patterns, patterns with just 2 variables, patterns of length greater than 118 can be avoided on the binary alphabet. So this 118 is probably not optimal, but it seems quite difficult to improve this substantially. Here's another generalization, even further generalization of an abelian repetition. So in an abelian repetition, we wanted that the number of occurrences of each letter in the repeating blocks should be the same. Here's something even stronger. This is a result from a few years ago. So these guys, they showed that there exists an infinite word over this, this alphabet here, with the property that you never see 3 consecutive blocks whose entries sum to the same value. So you'll notice that this is stronger than being an abelian cube, because you must avoid a abelian cube to have this. Right? 'Cause if you have an abelian cube, then certainly they will sum to the same thing. But it's even stronger, right? Because possibly these blocks can sum to the same thing without being an abelian cube. So avoiding this is even stronger. And so they were able to show that the word generated by iterating this morphism has this property. And this is not easy. The proof of this is quite difficult. So here's an open problem. Can you prove the same result for these so-called sum squares? So can you avoid having 2 consecutive blocks that sum to the same value, right? So they proved it for 3, right? This sequence, you never see 3 blocks that sum to the same value. Can you prove the same result for 2 blocks?
Can you choose arbitrarily subset of integers?
Yes.
As your letter?
Yes. Any arbitrary but finite. Yes. And okay, so that's a good place for me to stop for the first part. So we take a break. Okay, so looks like we're ready. So, new topic again. So, I guess what I have shown you so far, you could call it more or less classical stuff, right? It's, you know, most of those results are based on, I guess, some standard, well-known techniques involving morphisms and so on. But there are some other very nice, more recent techniques for proving results in avoidability. And these kind of techniques, well, there's some very nice non-constructive methods. All right, so, you know, probabilistic arguments or some other kind of counting or existence type proofs that don't necessarily explicitly produce an example of whatever kind of word we're looking for. Right, so, okay, again, the general problem. We have some collection of words S that we are trying to avoid, right? So we would like to know, does there exist an infinite word over some finite alphabet that avoids this set S? And this set S could be squares, it could be abelian squares, it could be cubes or whatever we like. Now, there's one minor technicality. In these kind of non-constructive results, most of them will give you some kind of statement of the following type. There exists arbitrarily large finite words that avoid squares or cubes or whatever you're trying to avoid. How do we deduce the existence of an infinite word in this setting? It's not particularly difficult. In all of the examples I showed you previously, where we were iterating some morphism, it was more or less clear because we were producing some longer and longer sequence of prefixes. All right, so it's easy to understand what the infinite word should be. With some of these probabilistic methods, it's maybe not so clear because the result will simply say, oh, there exists arbitrarily large words that avoid whatever, and now it's not necessarily clear that there are some sequence of prefixes, but in fact, this can be deduced in a very standard way. So we have this, this result here called Koenig's lemma. It's basically a sort of compactness argument, which says that, well, if I have an infinite collection of finite words, I can find an infinite word where every factor is a factor of some word in my set X, right? So if I have arbitrarily large square-free words, then there's an infinite square-free word, right? So I won't say too much about that. It's a pretty easy argument. But just that by itself is already a non-constructive result, right? Because, you know, the theorem says there exists an infinite word, but it doesn't tell you anything about how to construct it. Let's just make the observation that that result can be strengthened a little bit in the following sense. For various reasons, certain people who are working in symbolic dynamics or other things, they would very much like to have recurrent words for what they're doing. And a recurrent infinite word is a word where every factor of this word recurs infinitely often, right? And a word is uniformly recurrent if every factor recurs infinitely often at some bounded distance. Right? And so, somewhat surprisingly, that claim of Koenig can be improved to show not just the existence of an infinite word, avoiding whatever, but in fact, you can show that there exists a uniformly recurrent infinite word that avoids whatever. And so this was proved by Furstenberg. And there are many different ways to prove this. So, one of the first uses of the probabilistic method to prove some kind of avoidability result was this result of Beck in 1981. Okay, so you can read it. What it's saying is that, basically it's saying that the distance between two consecutive occurrences of the same identical factor in this infinite word W is exponentially large, right? So I have some factor of length n. The next occurrence of that same factor of length n is at some exponentially large distance away, right? For all n sufficiently large, so it's some kind of asymptotic result. Right, so obviously for small factors you will have some repetition at fairly close distances, but for large enough factors, right, the distance between consecutive occurrences of any factor of length n is exponential in n, right, which is a very strong avoidability result, right? So I mean, when we were avoiding squares, we were just avoiding repetitions where, you know, the one thing was right next to the other one. But now we're avoiding all repetitions where the two repeating blocks are, you know, some distance away. We're saying that, you know, the next repetition must be really very far away, right? So this is a very strong result. And it was proved using a technique from probabilistic combinatorics called the Lovász local lemma. And Arseny told me that in a previous school here that there was a series of lectures given on this Lovász local lemma, and that many of you probably were also at that school, so you should remember something about this Lovász local lemma. Now, I will not say too much about the classical Lovász local lemma, but I will talk about some more recent generalizations of that kind of technique. So the point of the Lovász local lemma is it's just a lemma in probability theory that gives you some bounds on the probability of the intersection of some events where these events are not necessarily independent. Right, there's some dependency among the events, but relatively small, that can be controlled, and then this Lovász local lemma gives you some bounds on this probability. And the way it works in combinatorics on words is, let's say you want to generate randomly a square-free word, so you consider a random word and then look at the probability that a certain factor is a square. But then, of course, there will be other factors that overlap, right? So you'll have some dependencies among the probabilities that a certain factor is a square. So this Lovász local lemma works nicely in those kind of situations. And then a few years ago, Moser and Tardas gave an algorithmic proof of this Lovász local lemma. And the proof technique that they used, people have been calling it the entropy compression method. And so this was a very sort of influential paper. And after it was published, many papers and results were proved using this technique. And well, the technique is actually quite simple. It gives, in most cases, I think it gives stronger results than just using the classical Lovász local lemma. And it works very well for problems in combinatorics on words. And it seems to give somewhat sharper results. So here's an example of a result that can be proved using this method. This is some kind of, if you are familiar with list colorings in graph theory, this is basically a list coloring result for words, right? So the idea is you want to construct a sequence, and at each position you have a list of alphabet symbols that you're permitted to use at that position, right? And you specify this list at every position. And so these guys, they prove that if your lists have size 4, then whatever the specification of lists, you can always construct an infinite sequence that obeys this condition, right? That each symbol Si belongs to the ith list, right? So in particular, if you choose your list at every position to be 1, 2, 3, 4, then that result simply says that there exists a square-free word over a 4-letter alphabet, right? So, okay, we know that there are square-free words, infinite square-free words over a 3-letter alphabet. So this 4 is not optimal, but it's a good example of the technique. Okay, so here's how it works. So people for a very long time have realized that if you are trying to figure out if some kind of repetition is avoidable, the first thing you usually do is you write a computer program to see if you can find some long occurrences of a word avoiding whatever squares or whatever kind of repetition you are trying to avoid. And the obvious computer program that you write is a backtracking algorithm, right? So you try to build a word one symbol at a time. So let's say you've built a square-free word of this length, then you try to extend by one symbol, and if it works, great, you keep extending, right? And so, well, if you try to extend by a letter A and it doesn't work, then you try letter B, and if it doesn't work, you try letter C, and if all those fail, then you back up, right? And you change some earlier letter, and you continue to try and extend, right? So that's the obvious computer program that anybody would write if they were trying to find long square-free words, right? And so the nice thing about this entropy compression method is that it basically says, do this kind of backtrack, do it randomly. So when you extend, you choose at random what letter you're going to extend by. And if it works, you continue to extend. If it doesn't work, so if you try to extend and you create a square, XX, you delete the second X, and then you continue to try and extend from there, right? So you have this algorithm, right? Very simple backtracking algorithm, right? We try to extend. We extend by a symbol chosen at random. And if it works, we continue. If it fails, we delete the square that was created, and we continue running the algorithm. And so essentially the proof says that if we run this randomized backtracking algorithm, if we run it for long enough, we will produce a square-free word of length n, right? If we want to produce a square-free word of length n, it's enough to just run this algorithm for long enough, and with positive probability, it will produce a square-free word of length n, right? So that's what we have to try to prove, right? That for every n, if we run this algorithm for long enough, with positive probability, it produces a square-free word of length n. Okay? So we fix some n. We want to say something about whether or not there exists a square-free word of length n. So let's count how many possible executions there can be of this algorithm, right? It's a randomized algorithm, so there will be several possible executions. Well, okay. Let's let m be the number of insertions. So this happens here at step 3, where we extend by some randomly chosen r. So let m be the number of these insertions made during the execution of the algorithm. And okay, let r1, r2 up to rm be the sequence of insertions that we make. There are 4 to the m such sequences. And if I know that sequence, I know what the algorithm does, right? So those sequences of choices, that tells me exactly what the execution of the algorithm was. So there are 4 to the m possible executions. Okay, so now we're going to count this in a different way. Okay, so we're going to count the number of executions of the algorithm in 2 different ways, compare these 2 quantities, and get some kind of contradiction. Okay? So this is again going to be a proof by contradiction, right? I claim that for this n, if I let the algorithm run for long enough, it will produce a square-free word of length n. So I'm going to show this by contradiction. I'm going to say that, well, suppose I do run it for a very long time, and it does not produce a square-free word of length n, then I get a contradiction. Okay? So I have this one way of counting the executions of the algorithm, and now I count it a different way. To describe, essentially this way of describing the algorithm kind of works in reverse. So suppose I know the sequence S that was the final sequence S. After m steps, the algorithm stops after m steps and has generated a certain sequence S. So suppose I know that, right, the final sequence S, and suppose I know the time and the length of each deletion that happened during the execution of the algorithm. Right? So I claim that from that information I can uniquely reconstruct the execution of the algorithm, right, using this piece of information, the final sequence, and then the times and the lengths of each deletion that happened. So remember, a deletion happens whenever I try to extend and I create a square. I then delete the second half of the square. Right? So I record every time that a deletion happens, and I record the length of the word that was deleted. So the point is, of course, that if I have this information, I can run the algorithm backwards using this information, right? I can reconstruct the algorithm by running it backwards, because whenever a deletion happens, remember, a deletion is the second half of a square. So if at a certain point I know that a deletion of length L took place, I can regenerate the block, the deleted block, just by copying the suffix of length L that I have, right? I just copy it, and I get it back. And so then I just keep running the algorithm backwards. And I reconstruct everything that happened during this execution of the algorithm. And the most convenient way to keep track of the lengths of the deleted blocks is to make this picture, right? So suppose the algorithm goes like this, right? So I start with a 1, I extend with a 2, I extend with a 1, and then I extend with a 2 again. Oh, but that created a square, right? So I have to delete the second 1, 2, and I get this 1, 2, and then I extend by a 3, and so on. Right? Well, I just make this picture that tracks the length of the word, right? I extend, I extend, I extend, I extend. Oh, and then here I delete 2 characters, so I go down by 2, right? Then I extend, I go up, and if I extend, I go up, and if I delete, I go down, right? And then finally, at the very end, I just go down to the x-axis. Right, so if I stop with a word of length I just terminate the whole thing by going down to the x-axis. Right, so it's clear that if I have this picture, I know exactly what time a deletion occurred, and I know what length the deletion was, right? So now the point is that then the sequence of deletions is represented by a so-called Dick path of length 2m, right? And wow, the total number of all such paths is given by the mth Catalan number, just like that. And so remember that the execution of the algorithm was uniquely determined by the final sequence S, which is some string of length less than n. And this Dick path, right? So there are at most, let's say, this many strings of length less than, I guess this would be less than or equal to n. Maybe I should change that exponent, but anyways, you get the idea. There are most this many sequences S that I can end up with, and then there are at most this many of these dict paths that count insertions and deletions. This is maybe overcounting because it's not necessarily all dict paths will correspond to what this algorithm is doing. But in any case, this is an upper bound. Right, so there are this many possible executions of the algorithm. So I have these two different counts for numbers of executions of the algorithm. Okay, so now here's the proof by contradiction. Suppose the algorithm fails to produce a square free word of length n. Okay, so I let it run for a long, long time, and it fails to produce a square free word of length n. Well, I know that if it runs for m steps, there are this many executions of the algorithm. And I also know that there can be at most this many executions of the algorithm, right? This guy here counts final strings of length less than n. And this part here counts the dict paths. Right, so this quantity here is at most this. Okay, well the asymptotics of the Catalan numbers are well known. Right, they grow like this. And so now we simply observe that in fact this inequality cannot hold. Right? Because I got this factor of, I've got 4 to the m here, and then I got 4 to the m here, but then I've got this m to the 3/2 in the bottom there. Right? So this inequality cannot hold for m sufficiently large. Right? So I get a contradiction. Right? So in fact, if I choose m sufficiently large, if I let the algorithm run for long enough, with positive probability, the algorithm produces a square free word of length n. Right? So that's how the algorithm, that's how the technique works, right? It's actually very simple, right? You have some backtracking algorithm, you come up with some kind of data structure to count the number of executions of the algorithm, and then you make this kind of argument to show that if the algorithm runs for long enough, then in fact some execution of the algorithm must produce a square free word of length n for every n, right? Okay, so like I said, this proves that there's a square free word of length n over 4-letter alphabet. So there must be an infinite square free word over 4 letters. Now, as we said before, obviously we know that you can avoid square free words over 3 letters. So this result is not optimal. But this method is and has been quite effective for showing avoidability of some more complicated kinds of patterns than squares. Right? So let me give you some examples of some results that have been proved using this method. So here's a result about avoiding squares in arithmetic progressions again. So these guys proved that there are arbitrarily long sequences over this many symbols, 2k plus some square root k number of alphabet symbols, that avoid squares in every arithmetic progression whose difference is either 1, 2, 3, 4, whatever, right? All those arithmetic progressions of difference 1, all arithmetic progressions of difference 2, 3, up to k, those are all square free. Right? So you need roughly this many alphabet symbols, and you can do it. Okay, here's another example. This is some kind of online, if you like, generation of square-free words. It's kind of formulated as a two-player game where the two players are going to build some infinite sequence, and player one, he would like to build a square-free sequence. That's his goal. His goal is to try to avoid squares, and player two, his goal is to try to create squares. Right? And so they play this game by, well, on each player's turn, he has to extend the current sequence by one character. Right? So player one, he extends by one character. Player two, he extends, and they're fighting with each other. One of them is trying to create squares. One of them is trying to avoid squares. Now, obviously, player two can just repeat the last symbol that player one played and always get a square of a single character repeated twice. All right, so that there's no way to avoid that. But it is possible for player one to play forever while avoiding all squares except for those trivial ones. All right, and he can do it if he has a 6-letter alphabet. All right? So if he has a 6-letter alphabet, player one has a strategy that he can play forever. And all player two can do is create those trivial one-character repetitions. So that result was proved again using this method. One of the results I told you about yesterday, about the avoidability of patterns. Remember, I gave you a result about the avoidability of long patterns. All right, patterns with k variables of length 2 to the k are avoidable over a 3-letter alphabet, and so on. So that result was proved independently by 2 different sets of authors, and one of those sets of authors used this entropy compression method to obtain that result. So it's a very powerful technique. Here's another one. So here's another technique for showing the existence of words avoiding some set S. So this comes from a paper of Miller, 2011. So again, I have some set S of words to be avoided. And okay, I have this criterion. Suppose there exists some real number c less than 1 with the probability that this sum is less than k times c minus 1. Okay, so k is the alphabet size, c is some constant less than 1, s is the set of words to be avoided, and I make this sum, c to the length of s, summed over all words s and s. If this sum is smaller than this quantity, then there exists an infinite word avoiding the words in S. Okay? So that's this is just some inequality involving the lengths of the words that I'm trying to avoid. I don't care what the words are, all that matters is their length. And if this happens, then I can avoid the set S. Okay, so here's how the proof goes. Okay, I have a k-letter alphabet. Let's use the letters 0 up to k minus 1. Let's call that sum that appeared on the left-hand side of the inequality, let's call it p. And okay, suppose the inequality holds. P is less than k times c minus 1. Now, my goal is to build an infinite word, avoiding this, this set S. So I'm going to start with the word x. And suppose that x has the property that this complicated looking sum is less than 1. Okay, so what does the sum mean? Okay, so first of all, the inner sum, what I mean here is just to sum up all the elements of this set, right? So just add up all the c to the u's, where the u runs over all u's that satisfy this condition. and then take the outer sum over all S and S. So, okay, what exactly does this mean? I have this word X, right? Now, possibly there is some suffix U, or there's some suffix of X that can be completed to form a forbidden word from the set S, right? U is the extension that I need to create that forbidden word S, right? So X ends in some suffixes that can possibly be extended to create some bad forbidden word, okay? And so I'm going to take this sum over all such, take the sum of C to the length of U over all such U, right? So the idea of this quantity Wx, the idea of it is, as I say, it's some kind of weight, and it's measuring these kind of pending threats, right? So I'm extending X, and there's possibly some threat that if I extend, I will complete some suffix to a forbidden word, right? So these are some threats. And this quantity Wx measures how close I am to creating something bad if I extend, okay? And the point is, as long as this W of X is less than 1, X must avoid S. Because if X did contain a word in S, then I could take U to be the empty word, right? I could take the empty word as an extension, and then X would create, X would end in this S, and then I would have C to the 0, and this whole thing would be at least 1, right? So I have this word, and I'm going to build it by extending one character at a time, and at each step I'm going to extend by a character such that the weight of my sequence is always less than 1, right? And if I do this, I know if at every step I preserve the property that the weight of my word is less than 1, then I know that that word must avoid the words from S. Okay, so now here's the important step of the proof. So I have to show that if I have a word X with weight less than 1, there always exists a choice of letter to extend it such that the extension also has weight less than 1. And then once I show that, then the process just continues forever, and I can generate an infinite word. Okay, so let's look at all the possible extensions of X. So I claim that I have this formula. All right, if I sum W of XA over all extensions A, that is equal to Wx over C plus P over C. So why should that be true? Okay, so the point is, if I extend my word X by a letter A, that might match the first letter of an already pending threat, right? So I have this suffix that can be completed to a forbidden word, and I stick in this A that already matches the first letter of that extension, right? So I'm getting closer to creating a bad word from S, right? So this is what I mean by matching the first letter of an already pending threat, right? So I have some suffix that already can be extended, and now I've added the first letter of that extension, so I'm now getting closer and closer to producing the bad thing. Now this extension A might also be the start of a brand new threat, right? So these two things can happen. And when the first thing happens, that causes the weight of all the pending threats to go up by a factor 1 over C. If you go back to the definition of the weight, right? This U all of a sudden, the length of the extension shrinks, right? So this thing goes up by a factor 1 over c, right? So this is what happens whenever the pending threats, whenever A matches the first letter of a pending threat, and if A creates a brand new threat, it adds this much as the weight for the newly created threats, right? So that's why I get this, this equality here. Okay.
Recall, what is P?
P was this sum. Right? So this essentially is the sum of all brand new threats that could be created. But when I add the A, I already have the first letter of it. So I add P over C. Right? Okay. So I get this this thing here, right? Wx gets multiplied by a factor 1 over c, and then I add P over c. Now, the hypothesis was that W of x is less than 1. So Wx plus P is less than 1 over P. 1 over P, again by hypothesis, is less than K times C. Right, because P was less than K times C minus 1. Right, so this quantity is less than K times C. So that means if I divide through by C, right, I get that Wx over C plus P over C is less than K. Right? So this sum here, the sum of Wxa over all extensions A is less than K. But that means one of these A's, one of these terms in the sum must be less than 1, right? Because if they were all bigger than 1, the sum would be bigger than K. So one of these terms in the sum is less than 1. So that means there is a letter A that I can stick on the end such that the weight of Xa is less than 1, and therefore I can continue this extension process forever. Right? So that's how it goes. Okay, so that was the proof of the criteria, right? So it's just this simple inequality involving the lengths of the words that you're trying to avoid. So let's see how to actually apply it somehow. Here's one very simple application from Miller's paper. Suppose I give you a set of binary words that contains one word of length 5, one word of length 6, one word of length 7, one word of length 8. Right? I don't care what the words are. You can pick any words you like. Right? It's one word of length 5, one word of length 6, and so on. Then that set is avoidable on the binary alphabet. Right? Whatever the words are. So we have to check the criterion, right? We have to compute this sum, right, over all words S in S. And we have to show that this sum is less than 2 times C minus 1. Right? That was the inequality. Okay, so let's see what this sum looks like. Well, of course, it's okay. It's C to the 5 plus C to the 6 plus C to the 7, right? Because there's one string of every length greater than 5. Okay, so that looks like this. And now, if I pick C equal to 0.6, then this inequality is satisfied, right? This sum here is 0.1944, and that's less than 2 times C minus 1, right? So the inequality holds, and therefore this set of words is avoidable on the binary alphabet. All right, so the criterion is very easy to use, right? You just have to check these inequalities. Okay, let's go back to square-free words. Using this method, we can show that squares are avoidable over a 7-letter alphabet, which is not great. We've already seen how to do it on a 4-letter alphabet. We've seen how to do it on a 3-letter alphabet. So 7 is not great, but It's a nice example again of the method. So the set S of words to be avoided are the squares. Okay, I should make X non-empty here. Squares, right? We're avoiding the squares. So again, I need to evaluate this sum for an appropriately chosen value of C. So what does the sum look like? Well, okay, how many squares do I have? Well, okay, there are 7 to the I squares of length 2i, right? Over a 7-letter alphabet. And so I sum that over all I. So I get this, this expression here, which I simplify and I get this, right? And so now I need to show that for a suitable choice of C, that this thing is less than 7 times C minus 1. Right, I have to show that this is less than 7 times C minus 1 for a suitable choice of C, and the C that works is 0.22. Right, so C is 0.22, left-hand side is approximately this, right-hand side is approximately that, or exactly that. And so the inequality holds, and so again, squares are avoidable over a 7-letter alphabet. Right? Well, let's do one more. Let's avoid long squares over the binary alphabet. So again, it's a similar thing. Now our alphabet is k equals 2. We are avoiding squares xx, where the length of x is greater than or equal to 7. And I compute the same sum, but now I just start from I greater than or equal to 7. And my alphabet now is 2. So I simplify this, I get this thing here. And I have to show that this thing is less than 2C minus 1 for some choice of C. I take C to be this. I get this for the left-hand side, this for the right-hand side. The inequality holds. So that's, so those long squares are avoidable on the binary alphabet. Okay. Did I go to 12? Is that right? No? 3 minutes. Oh, okay. Oh, okay, let's see. How quickly can I do this? No, I can't do this in 3 minutes. Does everybody know what Kolmogorov complexity is? Then I can do it in 3 minutes. Okay. Skip, 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 skip. So, using that result of Miller that I just showed you, it's possible to give another proof of this this very nice result of Durand, Levin, and Shen, which says that, well, there exists an infinite word where every factor of this word has relatively high Kolmogorov complexity. Right? Where relatively high Kolmogorov complexity means that, well, each factor of this word has Kolmogorov complexity bigger than some alpha times the length of u, where alpha is some arbitrary real number that you can choose as close to 1 as you like, but not equal to 1. Okay? So that's quite a nice result, I think, right? So there's some infinite word where every factor has pretty high Kolmogorov complexity. All right, and this is the prefix Kolmogorov complexity. So I'll just quickly show you the proof. So it's very simple. To get the word that you want, you construct a word avoiding all the low complexity words. Right? Okay, so what are the low complexity words? They're all the words S whose Kolmogorov complexity is less than alpha times length of x minus some constant beta, some constant b. Okay? So those are the low complexity words. We avoid them, right? Then our infinite word, all the factors have high complexity. So we have to, again, we apply the same criterion of Miller. right? We compute this sum c to the length of s over all s and s. And we have to show that this is less than 2c minus 1. So, what does this sum look like? Well, if I choose a c to be 2 to the minus alpha, then okay, I substitute 2 to the minus alpha here. Now, by hypothesis, alpha s here is greater than ks minus b. All right, so this sum here is less than this sum here. I take out the 2 to the minus b. I'm left now with this sum, 2 to the minus ks over all s and s, but I can just as easily take the sum over all s and get an upper bound, right? And now I apply Kraft's inequality to this sum, right? By Kraft's inequality, this sum, if this is the prefix Kolmogorov complexity, right, then Kraft's inequality says that this quantity computed for a prefix code is less than 1. So this whole thing is less than 2 to the minus b. And now you just check that 2 to the minus b is less than 2c minus 1. Right, and so by the result of Miller, there's an infinite word avoiding this set S, which is the set of all low complexity words. Right? So it gives a very nice proof of this result. So, okay, these non-constructive results are very useful for many things. They've been used to prove things about, well, ordinary repetitions, patterns, approximate repetitions, and so on. For some reason, well, they do not seem to work for any kind of abelian repetitions. So, people have tried very hard, but it seems it doesn't work for any kind of abelian repetition. So there's some kind of limitation to these methods, but nevertheless they are very useful. So I think that's the end of my talk, and that's the end of my lectures for this school. So thank you very much for having me here.